Hello everyone, I'm Jessica from Aspyre, and today I'll be taking you guys through part 4 of our Algebra and Functions unit, Higher Degree Polynomial Functions. Today's math quote of the day is from Albert Einstein. Einstein says, "So far as the theories of mathematics are about reality, they are not certain. So far as they are certain, they are not about reality." Starting off with a definition of a polynomial function, polynomial functions involve non-negative integer powers of x with a non-zero leading coefficient. So in p of x as expressed here, a of n will have to be non-zero. A polynomial function has a domain from negative infinity to infinity, unless otherwise specified. And the leading term of a polynomial function denotes the highest degree of the variable in a polynomial function. If you look at the table at the bottom, depending on the degree of the polynomial, we have different specific names for that function. For example, if the function has a degree of 2, we call that a quadratic function. If the degree is 3, we call that a cubic function. If the degree is 4, we call that a quartic function, and so on. For the division algorithm, let's say you have two polynomials f of x and d of x. Let f of x be a polynomial with a degree of k, where k is not 0. And let d of x be a polynomial with degree less than or equal to the degree of f, which is k. Then quotient q of x and remainder r of x, both polynomial functions as well, will exist like below. We can express the dividend f of x as the product of the divisor d of x and the quotient q of x, plus remainder r of x. And r of x, or the remainder, will have a degree that is less than d of x. Next up, we have the remainder theorem. And the remainder theorem basically states that when a polynomial f of x is divided by a linear factor x minus a, the remainder will be equal to f of a, or the value when you substitute a into f of x. Looking at the example, we have f of x equals x cubed minus 2x squared plus 4x plus 5, and we're dividing by x minus 2. The remainder will be equal to f of 2, which is 2 cubed minus 2 times 2 squared plus 4 times 2 plus 5, or 13. For our first example, we need to find the remainder when 2x cubed plus 6x squared plus 5x plus 5 is divided by x plus 2. To find this result, we can use long division. So we first write the dividend, what we're dividing, which in this case is the cubic function, and then we write the divisor, or what we're dividing by, which in this problem is x plus 2. Then we start with the largest power terms and divide until we arrive at the result of 3 as a remainder. Note that we can also use the remainder theorem in this case by plugging in x equals minus 2 into this cubic function, and we'll get the same result. Next, we have the factor theorem. The factor theorem is used when factoring the polynomials completely or evenly. The theorem states that a polynomial f of x has a factor x minus a if and only if f of a is equal to 0. For example, if f of 1 equals 0, then x minus 1 is a factor of f of x. Looking at the example, we have f of x equals x squared plus 2x minus 8, which can be factored into x plus 4 times x minus 2. We can check that the factor theorem works by plugging in x equals negative 4 and x equals 2. And in this case, we get 0 for both results. For our second example, if x minus 2 is a factor of 3x cubed minus 5x squared minus x plus b, we need to find the value of b. And we can use the factor theorem to solve this. So if x minus 2 is a factor of this cubic polynomial, we know that if we plug 2 into the cubic polynomial, we'll get 0. So using that, we get 3 times 2 cubed minus 5 times 2 squared minus 2 plus b, which is the result that we get when we plug in x equals 2, equals 0. And through algebraic manipulation, we arrive at the result that b equals negative 2. Finally, we'll be looking at what end behavior is. The end behavior of a function f describes the behavior of the graph of a function at the ends of the x-axis. So when x approaches infinity and when x approaches negative infinity, which will usually be the case unless a domain is specified otherwise. and here n denotes the degree of the function. When the degree of the function, or n, is even, and a, the leading coefficient, is greater than 0, f of x will increase as x approaches infinity, and f of x will increase as well as x approaches negative infinity. And you can see an example of that over here. This is an example of a quadratic function which has an even degree of 2 with a leading coefficient that's positive, so it's going to face upwards. Now at the bottom, when n equals even and a is less than 0, f of x will decrease when x approaches infinity and when x approaches negative infinity. And an example of that is a quadratic function that faces downward, like this. Next, when n equals odd and a, or the leading coefficient, is greater than 0, f of x will increase as x approaches infinity and decrease as x approaches negative infinity. So we can see an example of that over here. This is a cubic polynomial. And when n is odd and a is less than 0, f of x will decrease as x approaches infinity and increase as x approaches negative infinity. And that's it. Thank you as always for your attention. We hope this helped. Next class we'll be moving on to part 5, which will involve exponential functions. Thank you.